continuation of what we studied yesterday. First one. One more question about the set-based algebra. Let me turn the light off. Just in case you need to know, here's your exam is what your exam is going to look like. There are 3 parts. Part 1 is made up of 6 short questions, each of which is worth 5 points. So that's a total of 30. And second part is all about Bayes theorem. That's 45. And the last one is 25. There are 3 questions under the Bayes theorem. The first one is the easiest, so you must get that one. Middle one, second one is about the middle level difficulty. But the third one is the hardest. So I recommend you to first definitely get the first 2, A and B, because that's a must. And third one is rather optional. So try all other questions first. And if you still have any time remaining, come back, return to this third question or this second part, and then try those credit assigned to that question. But again, that's hardest. Last one is about the probability distribution. Either the probability mass function or cumulative distribution function will be provided. And given that either PMF or CDF function, you have to answer the relevant questions. And one of those will be used as the practice question today. So 3 parts, the points are allocated accordingly. So spend your time in accordance with these point allocations to these 3 questions. So in total there are 12 sub-questions, which is add up to 100, which is the max score that you can obtain from this midterm exam. Date is 28, which is next Tuesday. You come right here and your exam will start at 10:30 sharp. There's no other classroom, no other class meeting at this place afternoon, so I don't know, maybe you can have like an extra 5 minutes or so if you need, but let's say that the exam is supposed to start at 10:30 and runs through the noon, 12. So you have a 1 hour and 30 minutes to work on these 12 questions. So that's what you're gonna have next Tuesday, a week from now. And then just the day before and then the lecture after the midterm exam, there's no class. So May 27th, there is no class, so don't come. And May 4th, which is the next lecture after the midterm exam again, I'm out of country. I'm coming back on May 9th, so that one is cancelled as well. And mega class will be scheduled either the last week of May or the first week of June. So the question is, there are 2 sets, A and B, and there's an independence between these 2. And then you want to decide whether the independence still holds between A and B complement this time. So this is another proof question. So no Venn diagram is okay. You actually have to go through that line by line argument and then just make it tight. Intuitively, this statement, the independence should hold. If there's an independence between A and B, and naturally there's also independence between A and B complement, because B complement depends on B, just a negation of B. So if there's an independence between A and B, should the independence hold between A and B complement? But proving something is different from just knowing it or guessing it or understanding it. So how do you start? Again, in proving certain things, there is no golden rule. The different ways can be tried. So I tried myself, but you certainly can try different ways. But one of the ways to go for this one is doing the partition of the set A, something like this. There's a one suggested solution, not the only one. Of course, you can do it different. So the way to partition this A, you must involve the second set B. So A, first write that as the intersection between A itself and the sample space, which is obvious, because sample space contains everything. So intersection between any set and the sample space is the set itself. So that's A. But then you must involve V into it. because you have to show the independence between A and B complement. So rewrite the sample space as the union of B and complement of B. And that also must be the case. So that's nothing but sample space. But you want to express the sample space involving the second set, B. But then the familiar property of the union and intersection, you can distribute them. So first, distribute the intersection to A, to B, put that in here, and then again apply the same intersection to the second set, which is B complement, and put that in the second parenthesis. And then of course in the middle of these two, there should be union. Nothing but the distribution of the union and intersection. So that's a one valid partition of this A, but you are involving this B into it. Clearly, first partition and second partition, they are independent, are not in disjoint, nothing in common, right? So the set here, A intersection B, and the A intersection B complement should be disjoint. No common elements that belong to both of these. Because in order to be in here, the element must belong to B, but then that means that that same element cannot belong to this, because that must belong to B complement, but that's impossible. So imagine that there's any element inside this set. In order to be in the first set, the element must be belong to B as well, because that's the intersection. But once it belongs to the first set, it cannot possibly belong to the second, because if it does belong to the second set, it means that that one also belongs to this B complement, but that's impossible. So that's why you know that it's disjoint. If you don't get it, try Venn diagram. So there's a sample space, there's a set B, and there's a set A. A intersection B is right here. I mean, of course, you're not supposed to use the Venn diagram for proving this, but at least you can get the idea. Check it whether that one is true or not. So intersection is right there. But then the second set, which is the intersection between A and B complement, it's nothing but this, the other part of this same set A. Right? So naturally they are disjoint. So B complement is anything other than B, so that's entire sample space except for this circle. And then intersection between that and A is of course the blue area. So in blue and red, obviously disjoint. Why do we emphasize that these two sets are disjoint? Because once you take the probability of both ends, probability of A, because of this equality that we just showed, should be the probability of the whole thing. But then the probability of the whole thing is the same as the sum of each probability because they are disjoint. One of the axioms that we covered in the first month. So P of the entire, this one, is the same as sum of each probability because of this disjoint between, being disjoint between the first set and then the second set, one line up. Okay. So we have this equality, but then we are almost done because A and B are known to be independent. So probability of A intersection B must be the same as the product of each probability of A and probability of B, which is nothing but the definition of independence. By moving the first term to the left-hand side, and then factor this P of B, because P of A is there, and same P of A is there. So first move this one to here, and then factor this P of B, and then what's remaining is this. And that is the same as this probability of A intersection B complement, but then the stuff inside this bracket is nothing but the probability of B complement. So you have just shown that A and B complement is also independent. Quite obvious. Right? So go through the lines of argument and check them line by line. You'll easily see that the argument is clear and tight. So when I was writing the exam over the weekend, I wrote 3 questions of this sort. This is one of those. So since I'm using it now here, won't be put on your exam. So this one was the hardest one. But the actual exam question that you get to handle is going to be easier than this, but then harder than what we did yesterday. So you remember that there was another question like this that we tried yesterday? So your actual exam question is harder than that, but easier than this. So one question involving this set-based algebra will be on your midterm, which is worth like 5 points or so. I mean, even if you don't get the 5 points, still you can get score high. So there's no problem if you can handle all the others well. But this is a bit different because this is an official proof. So many of you might find it rather uncomfortable. But maybe you want to invest more of your time into other stuff so that you can maximize your score from that part, if you believe that this is not yours. But I'm just letting you know that there will be one question like this one will be on your exam next Tuesday. Okay. Any comments or questions about this one? No? Okay. Let's go to the next one. This one's easy. Computation. Expected value and variance of x. When we know that expectation of x is 1 and the expectation of the x squared is 3, then it asks you to compute the variance of 10 plus twice x. Since this one's easy, do it now and then let's compare the answers. And again, a very similar question was put on your exam next Tuesday. Something very much like this one, but numbers are different. The slight difference in terms of what's being asked, but the way to get it is almost the same, so it's a good time to practice it. So first, use the useful representation of variance, which is nothing but the difference between e of x squared and ex squared, each of which is known to us. First one, e of x squared is 3, and e of x is 1, so you square it, same, still a 1. Subtract 1 from 3 and then you get 2, so that's the variance of x. But then you have to go for the variance of the linear combination of x, not just x. But then any constant that is being added and then you take the variance of the whole thing, you should drop it because variance not affected by adding or subtracting some fixed numbers. So 10, it's out of it. You just simply drop that. But coefficient is still alive. It's just that you have to square it when you bring it outside. Then variance of x, we already figured it out to be 2. So 4 times 2 is nothing but 8, which is quite easily done. So again, something very similar to this one will be on your exam, which is another 5 points for this. So what can be asked is, instead of giving you the value for expectation and second moment, I can instead give you mean and variance of certain random variable and then ask you what the value for this second moment is. Basically switching the position of this variance and expectation of this second moment. So there's a couple of different ways to try basically the same thing. But if you know how to handle this, handling some other things should be straightforward as well. All right. Questions? Questions? Okay. The next one is Bayes theorem again. Some of you stopped by my office yesterday and then requested me to come up with one more question, one more example about this Bayes theorem. So this is number 7. We already did like 6 different questions about Bayes theorem. This is it. I'm running out of topics. This is indeed the last one. So there are 3 examples given during lectures. You go back to the lecture note on the Bayes theorem. You'll see 3 examples. One was put on the quiz. You also have access to that one. Another was on the homework. You got another one yesterday during review, and this is number 7. All because of this, second part, which is worth nearly half of the points for the midterm, 45. So read the question carefully. Always the steps that you need to go through in order to answer anything related to this Bayes theorem. First, read the question carefully because this is tend to be rather long compared to others. And then the second step, name some events using some initials, and then relate those initials, events, to the final answer. So the final answer that is being asked is this probability here. And then bring in the Bayes theorem, figure out the correct numbers for either conditional probability or unconditional probability, and then compute those numbers. So you're playing cards. So randomly pick 3 cards out of 3 cards, of course. They are the same in terms of its form, but they have different colors. First one out of the 3 cards are all red on both sides. Second one is all black. Both the front and back are black. Third one is a bit unusual. They are different in colors. Front it's red, the other side is black. So first one is all red, second one is all black, third one is red and black. So given these 3 cards, you shuffle them, mix up them well, and then we'll pick up one card on a random basis, then put it on the table, and then you see that the color is red. Before you turn it upside down, you want to figure out what's the probability such that the other side is black. So it's a conditional probability. You randomly pick up one card out of the 3, see only one side, and that side that you are seeing is a red. And you want to figure out the probability such that the other side is black. So it's clearly conditional probability. And once you know that this is something about conditional probability, you immediately know that that's the right place to bring in the Bayes theorem. This one, in terms of the difficulty level, I would say this is almost the same as the middle one that we will get next week, B. So neither easy nor hard, but the medium level. So this is almost the same in terms of the difficulty. Of course, the question itself is completely different. So I think it's a good practice. I mean, if I just hand you the solutions, you don't think, you just write it down. So think about how to go for this one like a couple minutes. Because next week, nobody will be around you to give hints. So this is the last chance to practice. So think about how to go for this one like a minute or 2. First, name a few important events. Obviously here, like 3 events should be, chosen card is all red, that's one event. Second event could be the chosen one is all black. And third event could be chosen card is a red and black. And then there's another event. Chosen card, when you place it on the table, you see that the color is red. That should be the 4th event. And then desired probability, you can write it in terms of those initials, names of those events. And then think about how to set up the Bayes formula such that you can figure out this conditional probability. First, define a few events, like RR can be the event that you choose the all red card. BB could be named as the event could be named as BB if the chosen card is all black, and maybe RB for the third card, the event that the third one is chosen. And then the last event is the chosen card, its face is the red colored red. It's funny because the guy who asked me to come up with one more example of a Bayes theorem is not here today. How strange. He just came to my office around like 3 and then I need one more example of Bayes theorem. And then he's not here. So let's do it. So you can approach this way. First, name these 3 events. double R, double B, and RB respectively represent the events that the chosen card is all red. So this is the case when the chosen card is all red on both sides. Second event, chosen one is all black. And third event, chosen one is red and black. And then finally, you can define R such that that refers to the event that the upturned side of the chosen card is red, which is what we are observing. And final answer, ultimate answer we try to get, can be expressed in terms of these four events. That's nothing but given R, probability of RB. Because we observed that the upturned side of the chosen card is red. That's the uppercase R in this in here. And then the condition part, you want to figure out the chances that the card is indeed red and black. The other side must be black. Using the definition of conditional probability, you first write in terms of intersection of these two and then the marginal here at the bottom, numerator denominator, and then do the partition using these first three events, which is nothing but the law of total probability. So right there. The numerator is nothing but the multiplication rule, which is simple. So the hardest part is coming up with these three parts, which is the law of total probability. First, the conditional, given that it's a RB, probability that the upturned side of the card is R is half, because the other side is black. Probability of R given double R, knowing that the all red card was chosen, chances that the upturned side of it is also red is of course 1, because it's only red. The same 1/3 for the probability of double R. And then second conditional, given that the chosen one is a RB, we already figured it out there, so you just copy it down here. And then last conditional, knowing that the chosen card is all black, what are the chances that the upturned side is red? Of course 0. That's impossible, because it's all black. And then the similarly P of B, double B is also 1/3. So if you place these numbers into the right places, and you see that final answer should be 1/3, which is base theorem. So go over these 7 questions during the weekend when you have some time left. Must be busy taking multiple exams this and next week. We have 7 of them, 3 during lectures, 1 on the they're like a bunch of different questions were provided either during lectures, homework and quiz, and then during the review. So just go over those, and once you understand all of those 7 questions, you should be in the right shape to handle those 3 questions on the exam next week. All right. Next one. If you don't have any other questions about this. Probability distribution. So the last part of your exam is something like this one. Of course, the question itself will be different, but style should be rather similar. So define certain random variable, and here x is denoted by x, and refers to number of snowboards. You know what a snowboard is. People buy it and have fun on it during the winter time. There's a store, sports store, the big, large sports complex, and manager wants to figure out what's gonna be the sale of this snowboard in the coming year. So it's a random variable. Amount of sale takes any one of these 6 discrete values. So there's certain possibility that the actual number of sold snowboards for this coming year is 100, and that occurs with this probability of 0.04, which is rather small. It can be higher than that at 110 with increased probability of 16% chances. could be even bigger than that at 120 with even higher chances with 30% chance. And then the peak in this probability distribution comes at the value 130, 35%, and then the probability rapidly goes down as the value for X, number of sales increases to 140, and then finally the maximum value, maximum amount of sales that he is expecting for the coming year is 150, but that's gonna occur with a relatively low probability, just 6%. Right? So that's nothing but PMF. Why is it PMF? Because it's a probability distribution for the discrete random variable. It's discrete because you can count them. So it let us know what are the chances for each possible value for this X. So given this PMF, you're supposed to answer the following questions. Okay, first I write it down. So naturally, if you add up all these probabilities, starting from 0.04 all the way to 0.06, must be 1. Otherwise, it's not a valid PMF. But they add up to 1 in this case. Right. So given this PMF, we want to answer the following. Compute the expected value and variance of the variable X, which is easy part. So if you go ahead and do it, you'll get this one. First for the expected value. So you might want to have a calculator for this type. So exam itself is complete closed book. You are not allowed to bring in anything other than a pencil or pen, a razor, but you are allowed to bring some calculator, but no smartphone. Nothing that allows you to have access to the internet. But conventional calculator is good to use for questions like this. So multiply each corresponding probability by the realized value for X, and then you just go over all possible choices of those values for X. And that's nothing but the expected value. Of course, in the case of discrete random variable. So the exam covers lecture notes 1 through 6. Continuous case is ruled out. That one will be used for the final. So number 6, lecture on number 6 is the last one that you need to check. So all about discrete random variable. And another thing that I forgot to mention, maybe I did yesterday, some of those instructions, I got tongue-tied. Instructions in your exam could be quite lengthy, something like this one. Yeah, this is rather long. And if you don't understand any part of the vocabulary, you are allowed to ask. That's why there's exam proctor. So if she knows, I think she knows, she will tell you what the meaning of certain word or expressions. So last year what happened was there was an expression saying, so one question about gambling, and I said used the expression break even. You know what break even means? you play some gamble or game and then you broke even in the end. You didn't win, but you didn't lose. That's break even. But one student didn't even ask, and I thought that he was understanding it, but at the end of the final, just came up to me and said that I didn't know what the meaning of break even. But why? I asked him, why didn't you ask? He just said that, well, I didn't want to. But if you don't understand any part of English, just raise your hand and ask. If I'm around, I will be able to answer it. But this time I'm not near. But TAs will be there. So ask her. So that's the expected value, and variance is this similar kind of operation. Just first have to go for this expectation of x squared. Number gets big. That's another reason why you need to bring a calculator. Then you subtract the squared expectation of x, and the final answer for this variance is 134.91, which is quite straightforward. Next one. Continue with the provided PMF table. Now assume that the manager of this store orders somehow, this means 130 snowboards for the coming year. You want to figure out what are the chances, what is the probability that all of those 130 snowboards that the manager is going to order will be sold during the coming year. All of them will be sold. None of them will be left over. So what's the probability for that event? And of course you refer to the PMF table. This one's easy and quick to get the answer, so do it now and let's compare. Go back to the PMF and think about which one of those cases correspond to the case where all those 130 snowboards are sold out. There could be multiple choices, multiple cases, and figure out what to do about those multiple situations, multiple cases. So what do you get? Probability that all of those 130 snowboards ordered will be sold out. What are the chances? Look at the PMF table. Okay, let's figure it out. Should be 3 cases. So the demand for snowboards either equal to 130 or strictly bigger than that. In these 3 cases, all of those ordered 130 snowboards will be sold out. We should exclude the first 3, 100, 110, and 120, because demand is lower than supply in that case. They will be left over. So ruling out those first 3 cases, just need to take the probability for the last 3, which is the case when the demand is at 130, exactly the same as supply. All of them will be sold, or anything higher than that. 140 and 150 are the other 2 cases. Okay. Why do we add up these probabilities? So these numbers will be given by the table. Why do we add them up? Because they are disjoint. The first event, demand is at 130, is disjoint from the second event, demand that is at 140, because you cannot have both of them at the same time. It's not possible to have the demand at 130 and at the same time that you have a demand at 140. So that's why you add up. So the final answer should be 50% chances. No, these are separate cases. So that's the specific case when the demand is at 130. That's distinct from second situation where the demand is higher at 140. Those 2 are different. It's not cumulative. So that's one event. the demand is as high as 130, that's one thing. And then demand is even at higher number, 140, that's different. Any others? Okay. Last one for today and last one for the entire review for the midterm. Now the number of snowballs are ordered down at 120. But then what is the probability that some will be left over this time, which is the opposite of the previous case. Some of them will not be sold, will be left over and go directly to inventory. If anything left after selling them goes to inventory, so what is the probability for that when the number of snowballs ordered is just 120? This last one is actually the question that I got as a student when I was taking this same economic statistics courses 15 years back. So I just used it last year, but since I'm using it now, I have to change it slightly for your exam. But the style and format will be basically same. So what do you get? What's the answer for the last part? 0.20, 20%. Yeah, 20%. Yes, that only include the first two cases. Demand is strictly less than 120, either 100 or 110, and add up the probabilities for each, and then you get the final answer of 0.02. Any questions about this or anything else? I don't know what we did today. I'll be in my office between 1 and 4 because I have to teach a second class between 4 and 6 today. So I'll be in my office between 1 and 4. And the second class comes to an end at around like 6 p.m. If you ever want to stop by, do it before 9 because I need to go back home and packing for tomorrow's travel. So it's no fun. I mean, if you do it like 4 times every year, just the packing and unpacking becomes part of your life. And sometimes I forget to unpack, arrive here, and then just take the same bag to the airport, and then, which is no fun. So good luck. So you have one full week to prepare, and hope that you will do well. And then see you, all of you guys, next coming May 11th.